What if one strange galaxy could rewrite everything we thought we knew about black holes? What if the biggest ones in the universe didn't grow slowly, but were born in an instant? A new discovery hidden in plain sight may hold the answer. Chapter 1. The galaxy that shouldn't exist. There are moments in science when a single image can shake everything we think we know. The James Webb Space Telescope has given us plenty of those moments. But one recent discovery may be the strangest yet. It's a distant object, glowing softly in the depths of the early universe, shaped like an elegant sideways figure eight. Astronomers call it the Infinity Galaxy, not just because of how it looks, but because of what it might mean. Here's the strange part. This galaxy existed just 400 million years after the Big Bang. The data suggested that something at the center of this galaxy was releasing high-energy radiation. That's usually a sign of a black hole actively feeding, pulling in gas, heating it up, and blasting out light as it spins. This process is called accretion, and it's one of the best ways we have to detect black holes across the universe. But this one wasn't small. It wasn't average. It looked massive, supermassive. They're the monsters of the universe regions, where gravity is so strong, nothing can escape. According to most models, black holes start small, maybe 10 or 20 times the mass of the sun, and then grow by eating gas and merging with other black holes over billions of years. So, to find one this big in such a young galaxy didn't make sense. Something didn't add up. They're the cosmic toddlers of the universe just learning to exist. But this galaxy, it's different. It's organized, symmetrical, active. That's not what we expect from such a young object. Some have proposed it could be two lobes of gas orbiting a massive center. Others think it might be signs of a disk being twisted by a black hole's spin. Either way, it hints at something happening inside that's far more complex than random chance. It's like finding a fully developed city in the middle of a forest that's only just starting to grow. Not light, not matter, nothing. Usually, we think of black holes forming from the death of massive stars. Follow-up studies are already underway. Chandra X-ray Observatory has detected strong emissions from the same region, supporting the idea of a feeding black hole. Other instruments are now being aimed in that direction, trying to collect more data, confirm the mass, measure the spin, and understand the structure. Could the light be distorted by gravitational lensing, making it look more powerful than it is? A quiet defiance against what textbooks have told us. A reminder that the universe doesn't always follow our rules. Sometimes, it writes its own. Could it be two galaxies merging? All of those were considered, but none of them could explain the full picture. A fossil from a time before we thought supermassive black holes could even exist. A piece of evidence that changes the timeline of cosmic history. Light from this galaxy took over 13 billion years to reach us, a process that skips the slow build-up entirely, forming black holes in one sudden, dramatic moment. If that's what happened here, it could change how we understand the birth of galaxies, the structure of the cosmos, and maybe even our place in it. So when JWST captured its glow, we weren't just seeing a distant object. We're looking back through time to the very early days of the cosmos, back when the first stars were just lighting up, back when gravity was pulling together the first building blocks of everything. That the way we think they grow slowly, patiently, over eons doesn't apply in all cases. Maybe there's another way, a faster way, and if that's true, the Infinity Galaxy may be the first direct evidence of it. The energy output, the age, the mass, all signs pointed back to one thing. A black hole, already massive, already active, in a galaxy that barely had time to exist. But those are stellar mass black holes, tiny, compared to the giants found at the centers of galaxies. Supermassive black holes are millions or even billions of times the mass of the sun. And here's the problem. They take time to grow, or at least, that's what we thought. In cosmic time, that's barely the blink of an eye. And yet, hidden in its core appears to be something massive, something powerful, something that shouldn't be there, a supermassive black hole. Now, you've probably heard of black holes before. Astronomers noticed a faint object with a strange symmetry of glowing lobes connected in the middle, forming a shape eerily similar to the infinity symbol. The light was extremely redshifted, which told scientists that it came from a time when the universe was still young, around 400 million years old. That's incredibly early, a time when the first galaxies were just beginning to form. This infinity galaxy may have changed everything, because if what we're seeing is correct, then this supermassive black hole appeared far too early. There wasn't enough time for stars to live and die, merge and collapse, slowly building up into something this huge. It's like finding a fully grown tree in a desert where nothing should be had time to grow. And yet, there it is, quiet, mysterious, real. Let's slow down and take a closer look at what makes this galaxy so important. The first clue came from JWST's deep field imaging. What caught everyone's attention wasn't just the shape, it was the energy. This raised a huge question. How could a black hole that size exist so early in the universe? At first, scientists considered other explanations. Could it just be a very compact galaxy with a lot of star formation? So what does this mean? It might mean that the standard story we tell about black holes is incomplete. But before we go there, let us talk about why this galaxy's discovery is even more significant than it first appears. In astronomy, distance is time. The further we look, the further back in time we see. Most galaxies from that era are small, dim, chaotic, and then there's the shape. The figure-8 structure isn't just beautiful, it's strange. It suggests gravitational interactions we don't fully understand yet. This galaxy may not just be old, it may be unique. Of course, the discovery is still fresh, but no matter how the details play out, one thing is already clear. The infinity galaxy is a challenge. So as we move forward in this story, we'll explore the theory that might explain this mystery. Direct collapse. For now, though, one thing is certain. The infinity galaxy shouldn't exist, and yet it does. Chapter 5. The theory that could change everything. Let's step back. What if the infinity galaxy isn't just a rare case of cosmic curiosity? What if it's a sign that our understanding of the early universe is missing something huge? Here is the idea that is quietly gaining traction. Maybe the standard model of black hole formation, especially the part about them growing slowly from the collapse of massive stars DOS and T, applied to the very first black holes. Maybe, just maybe, there's a completely different mechanism at play in the early universe, one that doesn't require stars at all. This is where we meet the concept of direct collapse black holes. It's a theory that's been around for a while, mostly floating on the fringes of mainstream astrophysics. Could it have formed entire structures, galaxies, quasars, even dark matter hellish faster than we thought possible? That is, they didn't just grow alongside galaxies. What if these early black holes didn't deform inside the first galaxies, but the galaxies formed around them? Or is it the invisible anchor at the core, the black hole that gives everything else a reason to orbit? In this view, a galaxy isn't built from the outside in. It's seeded from the center out, like a pearl growing around a grain of sand. Some physicists believe that black holes might affect not just space but time as well. But at maximum, it could be a key to a version of cosmic history where black holes come first, where gravity, not stars, leads the way, where the dark corners of space aren't just empty but fundamental. It only gives us clues, and it's up to us to follow them, even if they lead us straight into the unknown. There is a lot more like this out there, stories that twist the laws of nature and flip science on its head. So if you're curious about what else is hiding in the dark, consider subscribing. Drop a comment. What do you think the infinity galaxy really is? And of course, leave a like if this mystery pulled you in. Until next time, keep questioning, and if those early black holes were forming in large numbers, scattered across the cosmos, their gravitational effects might have shaped the timeline of the universe in ways we haven't yet imagined. That's exactly what the infinity galaxy might be showing us. It means the first things to form weren't stars or galaxies. They were singularities, points of unimaginable density that shaped the cosmos like hidden engines, silent, invisible, and powerful. A supermassive black hole that existed before the galaxy around it even finished forming. The center came first, the structure came later. They shaped them. Black holes as architects, not just consequences. It flips the script we've been following for decades. Could the laws of physics themselves have behaved differently in those first few 100 million years? Every black hole, every lightless corner of the sky, every assumption we've ever made about how it all began. And if that's the case, then we have to ask ourselves how much of what we think we know is actually upside down. It also bypasses one of the most puzzling problems in cosmology. There is not enough time in the early universe for normal starborn black holes to grow into the giants we've observed. Direct collapse changes that equation completely, but findings like the infinity galaxy are pushing it towards center stage. According to this idea, in the early universe, some regions of gas might have been so dense and hot that instead of forming stars, the entire cloud collapsed directly into a black hole. One starts off massive right from the beginning. No star, no supernova, just ... a black hole, fully formed. If true, this could explain how the supermassive monsters we see today got such a head start. But the implications don't stop there. If the early universe could form black holes so quickly, so efficiently, what else could it have done? There's another, more radical theory emerging. Some scientists believe these early black holes might not just be the result of cosmic evolution but drivers of it. Now, take that and go one step further. This leads us to a fundamental question. What actually defines a galaxy? Is it the stars, the gas, the spiral arms? And if that's true, then it changes how we think about the universe's origin entirely. Here's another twist. If black holes formed first, it could also change how we understand time itself in those early moments. So what does the infinity galaxy truly mean? At minimum, it's a challenger sign that we're missing pieces of the puzzle. This isn't just about one galaxy anymore. It's about everything. The infinity galaxy might not be an exception. It might be the rule we never noticed, because sometimes all it takes is one strange galaxy to show us. The universe docent TOS simplicity. If this made you question what you thought you knew about the universe, you're not alone.
Chapter 4. The physics they didn't want to revisit. Here's where the story takes a strange, almost unsettling turn. After JWST's discovery of the unusual stream seemingly emerging from a black hole, theoretical physicists around the world found themselves scrambling not just to explain what was seen, but to protect the foundations of what they believe. But those models usually rely on matter being flung from just outside the event horizon, never through it. The web data told a different story. The signal was too steady, too linear, and most worryingly too aligned with where the black hole's event horizon should have been. For over a century, Einstein's general relativity has been the bedrock of our understanding of gravity, black holes, and could it mean that the event horizon isn't an impenetrable wall, but a kind of semi-permeable boundary one that behaves differently depending on energy levels, spin, or quantum states? Theoretical opposites of black holes. White holes spew matter and energy, but nothing can enter them. For decades, white holes were treated more as mathematical oddities than real astrophysical objects. But now, because if this observation holds and it wasn't or a data processing error, it means we may need to rewrite one of the most sacred parts of modern physics. It could mean that general relativity, while beautiful and effective, is incomplete in a way far more profound than we realized. Some are wondering if what Webb saw was a partial white hole or a hybrid something that violates our current categories entirely. Those usually spike and fade. This one was steady, like a signal. Conferences that once scoffed at alternative models now have entire panels dedicated to event horizon anomalies. Peer-reviewed journals are seeing a sudden uptick in papers revisiting failed ideas from the 1970s and 80s. And behind closed doors, NASA and ESA have reportedly begun commissioning simulations to test whether exotic black hole alternatives can explain the Webb data better than the standard models. It was background noise, and that might be the most humbling part of all. But some did begin revisiting obscure theories, ones that had been shelved decades ago because they didn't fit neatly within Einstein's neat space-time fabric. For example, there's the gravistar model. Gravistars are hypothetical objects that mimic black holes from the outside. The black hole wasn't even the primary target of that particular observation. It was an incidental object in the corner of a much broader survey. So this whole mystery, it might have been caught entirely by accident, but inside are filled with exotic energy, essentially bubbles of dark energy wrapped in a quantum shell. The final chapter explores where all of this might lead, not just for physics, but for humanity's place in the universe. They don't have a traditional singularity or an event horizon. What if JWST didn't capture a black hole at all but something masquerading as one? And that's exactly what got people nervous. Because when energy behaves like a signal, we have to ask what's sending it. Some fringe physicists have floated ideas like event horizon leakage or quantum tunneling black holes for years. They were laughed out of the room. But now, those very ideas are being quietly But this observation pokes at the one thing that has remained non-negotiable. Nothing escapes the event horizon, and yet, here we are. The mainstream explanation attempted to fold this anomaly into known accretion disk behavior magnetic field dynamics. Let's pause here. If light, energy, or matter can escape from inside a black hole, even partially, what does that mean for general relativity? And there's more. The strange ejection captured by Webb didn't fit the time signature of traditional outbursts. Of course, scientists weren't about to leap to alien hypotheses. Another fringe idea reemerged. The white hole. These theories aren't new, but what is new is how many respected physicists are now willing to publicly entertain them. But why such secrecy? Why the quiet funding of fringe ideas? And here's the kicker. JWST might not have been looking for this at all. Let that sink in. One of the most challenging observations of our time. Something that could change the laws of physics, ways, and T, part of any grand experiment. Because if something this important was hiding in plain sight, in the periphery of our attention, what else have we missed? Stay tuned.
Chapter 3. The direct collapse theory. So far, we've seen the mystery, a galaxy too young, a black hole too big, and a timeline that doesn't add up. If black holes grow from stars, there just wasn't enough time for that to happen in the early universe. So what's the alternative? That brings us to one of the most fascinating ideas in modern astrophysics, direct collapse. Instead of growing slowly from a dying star, what if some black holes were born big, not from a collapse of a single star, but from the fall of an entire cloud of gas? No explosion, no messy process, just gravity taking over everything at once. It sounds almost too simple, but it might solve one of the biggest puzzles in the cosmos. Let's break it down. These were the raw materials that would eventually form stars, galaxies, and everything we see today. The theory's been around for years, but for a long time, it was just that, a theory. Something interesting, maybe even elegant, but without direct proof. Until recently, we didn't have the tools to look deep enough into the universe's past to test it. But it also has to be stable in a very specific way. No fragmentation. That means it has to be extremely hot, so hot that atoms don't clump together. It also means there can't be too many heavy elements, like carbon or oxygen, which cool the gas and lead to star formation. The early universe had just the right makeup for this. Lots of hydrogen and helium, and not much else. If the gas breaks into smaller pieces, stars will form. And once stars form, their light pushes against gravity, heating the gas and stopping collapse. That kills the whole process. But under the right conditions, extremely hot, dense, and low in heavy elements, these clouds might never form stars at all. No stars, no cooling, just heat, pressure, and gravity. And then, not over millions of years, but in a single, catastrophic moment, a black hole is born, already massive, already hungry. Others say, we don't have enough data yet to confirm direct collapse, saying that the signals we're rereading could be and it explains how early galaxies might have grown around black holes, not the other way around. That's fair. This is a new frontier. The universe isn't giving up its secrets as but what if it's the opposite? What if black holes came first? What if they were the seeds that shaped everything else? Instead, the gas could skip that step, collapsing directly under its own gravity into a black hole. It was forming engines gravity wells that pulled matter in, shaped light, and created the cosmic architecture we see today. And direct collapse might be the ignition switch that lit the entire process. Sometimes they just appear, fully formed, quiet, and undeniable. In the early universe, space was filled with vast clouds of hydrogen and helium. This radiation can actually prevent other gas clouds from forming stars by destroying molecules like molecular hydrogen that helps cool gas and allow fragmentation. Without those molecules, the gas stays hot and smooth, and gravity can take over. That's when direct collapse can happen. In the last few years, more and more candidates have started to appear. Each one seems to show a black hole that formed too early, too fast, or in conditions that shouldn't have allowed it. And every time we find one, the case for direct collapse gets stronger. That's the idea behind direct collapse black holes, or DCBHS. For short, we'll follow the evidence, piece by piece, and see why scientists are starting to believe that direct collapse might not just be possible with JWST and Chandra. It shows signs of a massive black hole, but in a galaxy that's too young to have grown one through normal processes. And its structure smooth, symmetrical, with very little visible starlight looks. A lot like what simulations predict for a galaxy forming around a direct collapse black hole. We're starting to see things that match the predictions. No supernova. That's still far from a full-blown supermassive black hole, but it gives it a serious head start. One that could explain how galaxies like the Infinity Galaxy formed so early. No star life cycle, just one giant leap into darkness. This kind of collapse would create a black hole that is already huge, maybe 100,000 or even 1,000,000 times the mass of the Sun right from the beginning. And here's the twist. Scientists didn't just invent this idea to explain recent discoveries. But now, let's walk through what those conditions look like. To form a direct collapse black hole, a gas cloud has to be massive, millions of times heavier than the Sun. So for direct collapse to work, the gas needs to stay in one piece. But the key ingredient might be radiation. If nearby young galaxies are forming stars, they release strong ultraviolet radiation. So picture this, a massive, untouched gas cloud floating alone in space. That's the theory. And what makes it exciting is that we're finally finding objects that match this pattern. The Infinity Galaxy, with its extreme distance, unusual shape, and powerful energy signature, could be one of them. But it's not just this one object. Still, not everyone agrees. Some scientists argue that what we're re-seeing could be the result of unusual gas flows or rare galaxy mergers. But even skeptics admit the theory fills a gap. It offers a way for supermassive black holes to exist when they shouldn't. In fact, if direct collapse is real, it could flip our entire view of galaxy formation. We usually think of galaxies as the big picture vast islands of stars, with a black hole tucked quietly at the center. In that case, the early universe wasn't just forming galaxies. It's a bold idea. It breaks the rules. But the Infinity Galaxy suggests that maybe the rules were never what we thought. Because here's the truth. Black holes don't follow our time. They don't wait for stars to die. And the more we look back, the more we find. In the next chapter, we'll dive deeper into the data of what JWST and Chandra actually saw when they pointed their instruments at the Infinity Galaxy. It might be happening all around us. Chapter 2. The Supermassive Black Hole Paradox. Let's step back and ask a basic question. What exactly is the problem with this discovery? Why is finding a supermassive black hole in the Infinity Galaxy so controversial? We've been spotting supermassive black holes at the centers of young galaxies for quite some time now. According to our current understanding, black holes are supposed to grow slowly. A star collapses, forms a small black hole, and that black hole begins to consume gas and merge with others. It's a process that takes hundreds of millions, even billions of years. But in these early galaxies, like the one we now call the Infinity Galaxy, the clock hasn't even ticked long enough to allow that kind of growth. So how did something so massive show up so early? But that also takes time and a lot of perfect conditions, too many variables, too much luck. In fact, some of the brightest objects in the early universe, called quasars, are powered by black holes, 1 billion times the mass of our sun, shining less than 1 billion years after the Big Bang. We're seeing black holes that are too big, too early, in a universe that was still assembling its first galaxies. That might sound like a lot, but in cosmic terms, it's nothing. There's barely been time for stars to form, let alone die, collapse, and create black holes. And yet, in the center of this system, we see strong signals of a black hole that could be hundreds of millions of times the mass of our sun. That's not just surprising, it's a direct challenge to how we think black holes form in the first place. That shouldn't be possible, and yet, it keeps happening. Each discovery, like the Infinity Galaxy, gives us another piece. But sometimes, that new piece doesn't fit the picture we've been building. And when that happens, we have a choice. We can try to force the piece into our old model, or we can admit it's time to rethink the model itself. Well, it comes down to one big paradox, one that's been puzzling astronomers for years. The problem is timing. In fact, some scientists believe that the black hole comes first, and the galaxy forms around it. Its structure, age, and energy all point toward a massive black hole existing before any complex galaxy structure had time to develop. That flips the traditional view entirely. Instead of galaxies slowly evolving and forming central black holes, maybe the reverse is true. Triggered early star formation, accelerated the creation of galaxies, or even affected the cosmic web itself. They force us to confront the idea that the universe may be more chaotic, more efficient, and more alien than we assumed. Maybe black holes were the seeds, and galaxies the flowers that grew around them. This is known as the supermassive black hole growth problem, and it's one of the biggest open questions in modern astrophysics. In recent years, astronomers have spotted more and more early universe black holes that defy explanation. They argue that we might be underestimating how chaotic and dense the early universe really was. Maybe gas clouds were more compact, galaxies more turbulent, and matter more available than we thought. Or do we follow the mystery, wherever it leads? The Infinity Galaxy might just be the most dramatic example so far, but it's not alone. A process more extreme than anything we've seen, but possibly more common than we imagined. JWST, and even ground-based observatories, have all been building a case that our understanding of the first billion years of the universe might be incomplete. Maybe there's another path, something faster, more violent, more direct. And if that path is real, then the early universe may have been full of massive black holes forming in a completely different way than we ever imagined. Let's break it down with an example. You know, it takes years to grow into a full-grown oak. Maybe there was just more gas, or maybe the conditions were more extreme, allowing them to feed at nearly their maximum possible rate, the so-called Eddington limit. But even under ideal conditions, there is still a limit to how fast a black hole can grow without blowing away the very material it's trying to eat. Now, imagine coming back the next morning and finding not a sap, but a fully grown, 100-foot-old tree in its place. That's what it feels like to astronomers studying these ancient black holes. They simply appear, fully formed, far too early in the life of the universe. Imagine you plant a tree. There have been several attempts to explain this. Some scientists suggest black holes in the early universe grew much faster than we expected. Others propose that black holes could merge rapidly. If small black holes collide and combine over and over again, maybe they could reach large sizes quickly. The math just doesn't add up. Now, let's bring it back to the Infinity Galaxy. This object is estimated to have formed just 400 million years after the Big Bang. The Infinity Galaxy forces us to face an uncomfortable idea. Maybe we've been missing something. Maybe black holes aren't always born from dying stars. This idea isn't just speculation. It's backed by mounting evidence. Of course, not everyone agrees. Some researchers believe that with the right conditions, standard black hole growth is still possible. That's the beauty and the frustration of astronomy. We're piecing together a puzzle with limited clues. Here's why this matters. If our timeline for black hole growth is wrong, then so is our timeline for galaxy formation. Black holes and galaxies are closely linked. That's a radical idea, but not without support. The infinity galaxy might be the first clear example of a black hole first scenario. It raises deeper questions too. If black holes formed this quickly, what role did they play in shaping the universe? Could they have influenced the distribution of matter? These aren't just scientific questions. They're philosophical ones too. The paradox of the infinity galaxy isn't just about one strange object. It's about how we deal with the unexpected. Do we try to explain it away? In the next chapter, we'll follow it. Because if there is a faster way for black holes to form, one that skips the slow death of stars, then it may lie in something called direct collapse. And if it's real, it changes everything.